In this video, we're going to talk about classifying critical points. So let's recall that a critical point of a function f is a point where both the partial derivatives f sub x and f sub y are 0 or undefined. So let's imagine that we've got a surface represented by z equal our function. And suppose that we've found some critical points. So some of the critical points that we found might look like, say, that point there, maybe this point right here. So remember that we talked about the different types of critical points a little bit earlier in this video series when we talked about critical points. So some of the types are local maximum, where you've got a point that's higher than the surrounding points. You could have a local minimum, where your point is lower than the surrounding points, or you could have this sort of saddle point, where from one direction, let's switch colors here, from one direction this might look like a maximum, because you'd be climbing up to it, but from another direction it would look like a minimum, because you'd be going through a valley there. So those are the three types of critical points that we want to be able to classify in this section. So basically we're going to find a bunch of critical points and we're going to see a procedure for classifying which of the three types that point falls into. So we're going to calculate the second order partial derivatives of our function f, and specifically we're going to be interested in this quantity f sub xx times f sub yy minus the square of f sub xy. Okay, now this quantity, it's given different names in different textbooks, but let's just call that delta for the sake of giving it a short name here. And so classifying critical points is going to come down to calculating the value of delta for your different critical points. So this process of classifying critical points is called the second derivative test. And there are basically four different things that can happen when you calculate delta. First situation, if delta is a positive number and f sub xx happens to be positive as well, then your critical point is a local minimum. If delta is positive and f sub xx is negative, then your critical point is a local maximum. If delta is negative, then your critical point is a saddle point. And if delta comes out exactly equal to 0, that's the bad case. Then the second derivative test gives no information, and you need to look in more detail at your curve. So if that happens, try to figure out what's happening in, say, the xz plane and the yz plane and the xy plane, and you could do some further investigation in that way to try to classify your critical point. So let's find and classify all critical points. So this is going to involve taking our two partial derivatives f sub x and f sub y, and we're just going to ask, where are they 0 or undefined? Okay, so f sub x looks like 4 minus x squared minus y squared. That's never going to be undefined because it's a polynomial, so we're going to set that equal to 0. And then for f sub y minus 2xy, again, never going to be undefined, so we'll just set that equal to 0. Okay, now choose whichever one you think is easier to work with. I would say that's f sub y, and figure out what it means or under which circumstances this could equal 0. So there would be two cases, either x equals 0 or y equals 0. So we've done our investigation with f sub y already, and we'll figure out now what these two cases mean for f sub x. So if we call this equation 1 and equation 2, we've worked with equation 2, and we now need to sub the results into equation 1. So if we take x equals 0, sub it into equation 1, that would mean that 4 minus y squared is equal to 0. In other words, y squared is equal to 4, and that means y could be either plus or minus 2. So we're actually getting two possible critical points coming out of just that case. And we also need to now look at the case where y equals 0. So similar kind of idea, y equals 0 came from equation 2, so we need to sub that into the other equation, equation 1. That means 4 minus x squared could equal 0. And going through a similar kind of reasoning as what we just did, we could figure out that x equals either plus or minus 2. So that gives us 2 more critical points, plus or minus 2, 0. Okay, so now we've got 4 critical points, and this is the exciting part of this problem. We are going to classify these using the second derivative test. So I've just recopied the 2 partial derivatives at the top of the screen here because we're going to need these in this next part of the second derivative test. So usually what I like to do is just make a little chart. We're going to list our different critical points, which we found 4 of them. And we need to calculate that delta quantity. So along the way towards doing that, we're going to calculate f sub xx. We're going to calculate f sub yy. We're going to calculate f sub xy. And then from there, we can calculate delta, which is f sub xx, f sub yy, minus the square of f sub xy. And then once we've got that, then we can draw a conclusion. So we're just going to do this little table here for each of our 4 different points. And I'm just going to leave some room in here because we're actually going to be calculating these second order partial derivatives up at the top. Okay, so there we go. So let's put our points in here before we do anything else. So the points were 0, 2, 0, negative 2, 2, 0, and negative 2, 0. So I've just put them down here in no particular order. All right, so let's calculate our second order partial derivatives. F sub xx is going to look like negative 2x. F sub yy is also going to look like negative 2x, just sort of a fluke that comes out the same as f sub xx. And then f sub xy minus 2y. All right, so from there, we're going to fill in the table with some numerical values. So let's start with this point here. X is 0 and y is 2. And we're going to plug in to these second order partial derivatives. So negative 2x is going to be 0. Negative 2x, again 0, and negative 2y will be negative 4. Okay, so now we're going to calculate what happens if we multiply f sub xx times f sub yy and then subtract off the square of f sub xy. So we'd have 0 times 0 minus the square of negative 4. Well, that negative 4, when it gets squared, it becomes positive 16. So we're going to have a minus 16 here. Okay, so I think let's do the number part of the table while we're on a roll, and then we can do our conclusions at the end. So for the second point here, 0, negative 2, our values are going to be 0, 0, and positive 4. For x value 2 and y value 0, we're going to have negative 4, 0. And then when we've got x value negative 2, positive 4, 0. Okay, then let's calculate our delta quantity for each row here. So you're just going product of the first 2 numbers minus the square of the last number. That's going to be minus 16. This one will be positive 16 and another positive 16. Great. And so now let's think about our second derivative test. So I think I might scroll back to that quickly just so we can refresh our memory. So here are the rules up at the top of the screen. When delta is positive, you either have a local min or local max, depending on the sign of f sub xx. If f sub xx is also positive, it's going to be a local min. And then if delta is negative, you've got your saddle point. So immediately we can see there are a couple places where delta is negative. Saddle point in the top 2 situations. So saddle point and saddle point. And then in the bottom 2 situations, delta is positive. So we've either got a local min or a local max. You're going to have a local min when f sub xx is positive. So we got local min at the bottom, and we've got local max in the third situation. So that is how we classify critical points using the second derivative test. I just wanted to talk briefly about how the second derivative test works because the geometry is pretty nice here. So if you have a function where f sub xx is positive, what that's telling you is that in the xz plane, your function is concave up. And similarly, if f sub xx is negative, that's telling you in the xz plane, your function is concave down. So this is sort of similar to single variable calculus, where you'd say f double prime in single variable calculus. F double prime being positive corresponds to concave up, and f double prime being negative corresponds to concave down. Okay, so similarly, if we had something like f sub yy being positive, then we're talking about the behavior in the yz plane, because we're talking about the variable y, and f is giving us our z values. So yz plane is the appropriate perspective with which to be looking at this. And again, positive means concave up. Okay, so what that tells us, if you put these two things together, if someone tells you that f sub xx times f sub yy is positive, let's think about what that means in space. So it means the signs of f sub xx and f sub yy agree. Either they're both positive or they're both negative. If they were both positive, that means you'd have a bowl-like shape that's opening upwards. And if they were both negative, then you'd have a bowl that's opening downwards. Okay, so to say that f sub xx times f sub yy is positive tells you you're in one of these two situations. You don't know which one you're in, but you could then look at the sign of f sub xx, and you could say the sign of f sub xx determines which one you're in. If f sub xx is positive, you know you're in the first situation of the bowl opening up. If f sub xx is negative, you know you're in the situation of the bowl opening down. All right, now the only other piece of the puzzle that we need is just an understanding of what f sub xy measures. So let's talk about the absolute value of f sub xy, and let's say that when this is large, when it's a big number, that implies that f twists. And when we say twists, I'll just draw a picture to show what that means. So it means either your function is sort of concave up in the y direction, but concave down in the x direction, so like that, or the opposite type of behavior. So you could have concave down in the y direction and then concave up in the x direction. So that's what we're going to call twisting, like a saddle. So basically, when you calculate delta, what you're doing is you're trying to measure the dominant effect. You're trying to figure out, is this a stronger effect than this? And because you don't care about the sign of f sub xy, we actually just square it when we're subtracting it off. And that sort of also works out because in this case, you're multiplying two second order partial derivatives together. So by taking this quantity and then subtracting off the square of that quantity, you are figuring out the dominant tendency. If delta comes out positive, then this situation is winning, and you've got either a local min or local max. Whereas if delta comes out negative, then this situation is winning, and you've got a saddle point. So that's a bit of insight to the geometry as to how the second derivative test works. Thanks for watching.